Hello, welcome to another podcast of fractional derivatives. Today we're going to work on the fourth root of the derivative operator. The way we're going to do it is by taking the square root of the square root of the derivative operator. So let's do a recap of what has been done and how it can be changed. 1 second. Okay, so if you recall the last podcast, right? Maybe I need to change this a little more. There we go. Okay. Um, yes, so the square root of the derivative operator takes the 2 by 2 matrices over R, which is an algebra, it's non-commutative tensor over R, with the differential functions over R, that's a commutative algebra. And it gives you the 2 by 2 matrices over R, tensor over R, and this is just the functions on R basically. So, okay. So, and the way it's defined is that 1/2, right, acts on F, G, H, L tensor, let's call this M of X, right, to be equal to A tensor, the identity operator, plus B tensor, the derivative operator, acting on a typical element. Well, let's see here. We should make it consistent. Okay, now that we said that, where A is equal to, and now here's where we go a little bit change, a little bit different, I guess. Let's see here. A is equal to 0, 1, 0, 0, 0, and B is equal to 0, 1, 0, 0, 0, and AB plus BA is equal to the identity A squared equals 0, which is equal to B squared. Okay, so that's the recap from the square root of the derivative operator. Now we're going to do the square root of the square root, which will be the fourth root, right? So we want something a little different, actually. We want zi plus d derivative square has to be equal to ai plus b dx, right? So if we FOIL the left-hand side, we get c square I, well, that's tensor, I guess. This is tensor right here. This will be tensor here, and this will be tensor there, so CB plus, no, CB, CD plus, oh man, plus DC tensor derivative plus B square, or D square in this case, tensor D square, which is equal to, right. So what we want is the following. Yeah, so we want c squared equals a, d squared equals 0, and cd plus b plus dc equals b, basically. So yes, that's one way to do it, but it's rather complicated. So instead, what we're going to do is the following, right? Yeah, actually, just remember how to do it. Memory fails me, but no, I just remember. We're almost there. So let's rewrite this, right? So we want to take the square root of the derivative, right? So it's the same trick that we did for the square root of the derivative, except that this time this will be to the 1/2 square, right? I want this to be equal to I plus dx to the 1/2. Now the same mathematics that we used to derive the square root of the derivative applies, right? So we want, so the left hand side is equal to c squared I plus cd plus dc tensor dx to the 1/2 plus d squared tensor dx, right? And if we want both to be the same, then we get c squared equals 0 equals d squared, cd plus dc has to equal to I. So that means that uh, the algebra generated by C and D, right, over R, has to equal to the Clifford algebra 1, 1 over R, which is the same as the matrix of 2 by 2 numbers, 2 by 2 matrices, basically. And C has to equal to 0, 1, 0, 0, 0, and D has to equal to 0, 1, 0, 0, 0. Okay, so that's the square root, actually. And what does this mean is that we've extended the scalar of the scalar, right? So now to get the quarter root, right? We just combine both, right? So we get C tensor I, right? Plus D tensor, and here we go, A tensor I plus B tensor dx, right? So this ends up being equal to C tensor I plus D tensor A tensor I plus D tensor A plus, no, actually D tensor B. So come on, let's do this. It should work. Oh, it's because I'm pressing that, okay. How is this defined, right? These matrices, they belong to M2 of R, tensor over R, M2 of R, right? So, yeah, so, right, not sure what that space is, but that's what it is. So this happens to be isomorphic to, so this one's 2 square, right? This one's 2 square. So this is the same thing as M4R, basically. Yeah, so So yeah, so in order to get the fourth root of the derivative operator, we must take the we need 4 by 4 matrices as the extension of scalars. So, and these are the matrices that we want to use to define the fourth derivative operator, right? So, yeah, I hope you enjoyed this. It will be fun to extend. Well, in the next podcast, I'll do the derivation for the eighth, well, and then propose the derivation of 1 over 2 to the nth root. And then hopefully propose a formalism for the cubic root or any root, but it's going to be an infinite dimensional algebra instead of a finite dimensional algebra that's going to be needed. So yeah, so that will be exciting. And then hopefully in another podcast, we can explore solving a differential equation using the method of extension by scalars and see how memory comes into play with fractional derivatives. At least we can explore an article from the literature where they show that a fractional derivative keeps a memory of the dynamics of the system. So yeah, so thank you, and I will see you in another podcast. Okay.